Good morning everyone. Welcome to the third lecture of VLSI Interconnects course. Today we will be discussing what is called as the Elmore delay. Before we go into today's content, let us very quickly recap what we had seen in the previous lecture. In the previous lecture, we developed a distributed model for an interconnect, a distributed RC model. So we argued that the resistance of an interconnect is distributed throughout the length of the interconnect, and similarly the capacitance is also distributed throughout the length of your interconnect. And if you want to model an interconnect accurately, you need to take into consideration the distributed nature of resistance and capacitance. So we defined the resistance per unit length and the capacitance per unit length. And we did this modeling where we considered an infinitesimal section of your interconnect. We applied the voltage and current equations on this infinitesimal section, and we then applied the limit this delta x tends to 0 to finally get this diffusion equation. So we had seen that your voltage and also the current along the length of your interconnect is governed by what is called the diffusion equation. So in an RC interconnect, the phenomena with which the voltage propagates is actually the diffusion phenomena. We had also gone ahead and solved the diffusion equation by taking few cases, and finally what we had got was something of this series. So we had derived it on our own, but towards the end I had shown you this reference where the output voltage and input voltage comes out to be as a summation over large number of, or say infinite number of exponentials. So here was our problem. So your output voltage does not have a nice closed form expression anymore, and then we don't know that for such a output voltage, how would you define a simple RC delay? So remember, what is our goal? Our goal is we want a simple RC charging delay with closed form expression, and we found that it is difficult to define if your governing equation is a diffusion equation. Right, so for this it's very difficult. Let me refer you to another paper. This is from I think 1994. In this paper, there is a delay analysis of interconnects for using diffusion model, and so in this paper you will find this table where several of the different methods of approximating approximating or estimating the output voltage and the delay were given. So for a simple lumped RC model of interconnect, we have this expression. We had seen this in the first lecture. This is a simple lumped model, but this is approximate. Then there are other methods, like for example this method, which is an exact, but there is a summation. And then there is another method where it is approximated to 3 terms, and in this paper they have used this expression. So note that here, even though it appears to be a closed form expression, ERF is an error function, and error functions are computed numerically, and there are error function tables to compute that. So all these methods which were reported still had problems. Now remember, these simple expressions are for an interconnect like this. There is an input and there is an output. In practice, what we will be encountering would be a lot more complicated scenario where there would be branching of interconnect. So one input will not be mapped to a single input, single output node, but it would be feeding multiple output or say the load devices, right? So what we want is we want a reasonably accurate and a closed form expression to estimate the RC delay in the interconnect, in the branched interconnects and interconnect trees. We don't, I mean, if I have something for a simple interconnect, that is not enough, because my actual connections are a lot more complicated. And remember that what we want is we want a simple and closed form expressions. I don't want to go for full wave full wave simulations or solving a differential equation. So I can solve this. If I have an interconnect branch like this, I can solve the diffusion equation here numerically in this, but that would be time consuming, and I don't want that. I just want an estimate which I can use it for optimizing my layout or in the pre-designing process, right? And then later on, the final version, I can run a full wave simulation. But my immediate requirement is that I know the material parameters, I know the structural dimensions. From that I can get, if I get R and C, what would be my delay. That is my requirement, right? So with that, let us come to the today's lecture, which is Elmore delay. So the solution to this interconnect delay, branched interconnects and interconnect trees comes from a very old paper, which is from 1948. This was published in Journal of Applied Physics. The title is The Transient Response of Damped Linear Networks with Particular Regard to Wideband Amplifiers. So if you can see that this did not have anything particular to do with electronic circuits. In fact, this was, I think, first submitted in April 1947. 1947 is the year in which BJTs were invented. So this was not targeted for use in or estimating in delays in electronic circuits, but we will find that why this becomes so useful, right? So let us see what Elmore said, then we will come and see how that helps us in with the interconnects. So Elmore said that let us define the delay in a different way. So he said that if I have an output voltage E of t, so in his paper he is using the term of E of t. This is basically our V out of t. If I have an output voltage, this is the response to a unit step function. So it is a monotonically increasing. It is a monotonically increasing function, your output voltage. He said that okay, delay is something, I don't necessarily define it as a 50% delay or 0.63% delay. I define it somewhat differently. He said that let us take the derivative of the voltage. He said that let us take the derivative of the voltage. So your E of t is actually d V out d by dt, or this is also written as V out prime of t. Right. So he said that V out t is your output voltage. It forms a certain monotonically increasing response. If I take its derivative, it would be something like this. Now he said that let us define a delay. Let us define a delay as a centroid of the area under the curve dV by dt, or dV out by dt. So he said that this is my output, differentiation of output voltage. My Elmore delay is the centroid of this area under this curve, which is the derivation, which is the time derivative of my output voltage. So basically what he said was Elmore delay TD. He defined Elmore delay. He didn't use the term Elmore, but he said that this was the delay which we define, and that is integral. So what would be the centroid of this? Integral 0 to infinity t into V prime V out prime t, which is the derivative of your output voltage, into t divided by the total area under this differentiated output voltage, right? So this is how he said. So this is my output voltage. I just want to find the delay, and then you can see that this is mapped here, and then you can also define the rise time. He has defined the rise time. So This is how he defined TD. So if you look at this, so this is from his original paper, right? So please note that while defining this Elmore delay, he specifically said that this can be defined only for monotonically increasing functions of time. Why is that? Now it should make sense, because if your function is not monotonically increasing, then its derivative will have some negative part as well, right? So this is completely positive, but if this was not monotonically increasing, its derivative would have a negative term. And then if you are finding an area and solving an integral like this, there would be some term which becomes negative, and for that this estimate is inaccurate. So we need to ensure that you are if you want to use this Elmore delay as it is, then we need to first ensure that you have a monotonically increasing function of time. So with this definition, let us simplify this. We can simplify this further by just assuming that your final output voltage, so V out of infinity, is equal to 1. So the final value which this reaches is 1. So that would eliminate the integral in the denominator. Why? Because your V out of t is integral 0 to t V out prime t dt. And if I integrated V out of V out at infinity, you will have this integral. And if your final voltage is equal to 1, then your integrals will simply be equal to 1, integral for the denominator. And then you can define your Elmore delay as simply this integral going from 0 to t, 0 to infinity t V out prime t dt, where my V out prime, let me write it, is equal to dV out by dt, right? So you should go through these definitions and make your own notes with this. At this point you might be thinking, but why would I define a delay like this, right? I mean, if I recall my initial problem, I did not, first thing is that I did not have a simple closed form expression for my output voltage. So my output voltage was either coming as a summation, or it was an approximation, or there were complicated functions like error functions and all while defining this output voltage in the time domain. Now I am telling you that we take the derivative of that output voltage, multiply it by time, and then compute this integral to get an estimate of Elmore delay, right? So I don't see, if I'm looking at this expression like this in the time domain, that how will it solve my problem with the interconnects, right? This definition, in fact, actually it seems that it is more complicated. I have a V out of t which is an infinite series, and then I have to differentiate it and then integrate it, multiply it by time, integrate it, and then get my delay, right? So how is it going to help with interconnects, and more specifically with branched interconnects, right? So the solution to that is that we have till now defined this delay in the time domain only. Now let us again go back to the paper. Let us refer to the abstract of this paper. So in the abstract, Elmore says that when the transient response of a linear network to an applied unit step function, so the input is unit step function, and the output, that is the transient response, consists of a monotonic rise to a final constant value, it is found possible to define delay and rise time in such a way that these quantities can be computed simply from the Laplace system function of the network. So the key is these delay quantities can be computed very simply from the Laplace system function of the network. Laplace system function is nothing but what we call today as the transfer function of the system. So let us look at the systems model for a network, for an RC network. So what we have is this. I have an LTI system. In our case, this is an RC network, which can be my interconnect. The theory which we are looking at right now is more general for monotonically increasing output functions, or monotonic transient or say impulse response, or say unit step response, right? So your Vi of t is your input to this LTI system, and V out of t is your output, right? Your input is unit step function, so ut is unit step function. Now in the time domain, your output would be convolution of the input with the impulse response, but in the Laplace domain it's more simple. Your output V out of S is the transfer function times the input voltage. Now since your input signal is u of t in the time domain, in the frequency domain your Vi of S is simply 1 by S. Now if I substitute this Vi of S in this equation, my output voltage V out of S is 1 by S H of S. This is straightforward. I can rearrange this equation to get H of S as something like this. So H of S is S times V out of S, where I mean we should always note that here this is true when your input is a unit step function, right? So from the properties of Laplace transform, what we know, if Vi of t is your time domain signal, its Laplace transform is Vi of S. Similarly, V out of t is your time domain signal, so then your Laplace its Laplace domain representation is V out of S, right? Now what is the Laplace transform of dV out by dt? That is S times V out of S, right? If you differentiate in time domain, you multiply by S in the Laplace or the frequency domain, right? So your V out prime of S is equal to S times V out of S. So this is also straightforward. Now if I compare this with the equation here, H of S is equal to S times V out of S, right? Yeah, so I think I have written it here. If you recall, V out of S is this. So your H of S is nothing but your the Laplace transform of the derivative of your time derivative of your output voltage. I repeat, if the input to your system is a unit step signal, then the transfer function is equal to the Laplace transform of the time derivative is the Laplace transform of the time derivative of your output voltage. So your output voltage is V out of t, its time derivative is V out prime of t, and its Laplace transform is equal to the transfer function, right? Or yeah, this is what I was mentioning. Now by definition, if you look at the definition of Laplace transform, how do I compute the Laplace transform? I solve this integral, right? So this is my basic starting definition of my Laplace transform. So I have this integral going from 0 to infinity, V out prime t into e to the power minus st dt. I can expand e to the power minus st in the form of a Taylor series, and this would be my expansion. So if you are not familiar with this expansion, please go through the basics and recall how you get this expansion for e to the power minus st. I can substitute this in here and expand my integral. So I can write h of s as this integral 0 to infinity v out prime t into this term where there is an infinite series dt. Then h of s is equal to 0 to infinity. I am just now expanding these in different terms. So I can write this s comes out of this integral, and what remains inside this integral is t times, which is this t times v out prime t dt. Please derive this on your own so that you become familiar with what's going on. And then there are other terms, and these terms goes up to infinity. Now if we recall the previous definition of Elmore delay, simple definition of Elmore delay. What was my Elmore delay? Integral 0 to infinity t v out prime t dt. And now if you look at this term in here, you can readily notice that this is what is the your Elmore delay, right? This term here in h of s is your Elmore delay. So Elmore delay, then you can define in general. So if this is not equal to 1, then you will have to define it as a coefficient in general of minus times the coefficient of s to the power 1 divided by s to the power 0. So you have this h of s expanded as a polynomial of s. You take the minus times the coefficient of s to the power minus 1, s to the power 1 divided by the coefficient of s to the power 0, or that is a constant coefficient. Now if the final value of your output voltage is 1, then this term automatically, the first term automatically becomes 1, and then what you would have is simply hs is equal to 1 plus, or say 1 minus s into td plus this summation, right? So when the final value of voltage is 1, td is simply the coefficient of minus s in the expansion of h of s. So this definition which Elmore gave, that beautifully arises in this expansion, in the polynomial expansion of the transfer function in the Laplace domain, in the when we expand h of s as a polynomial of s. So this is my Elmore delay. This is what I am interested in. So with this, for a very complicated network also, it's always easier to define the transfer function. So it is always easier to define h of s. By this time all of you must be quite familiar with defining the transfer functions and solving basic networks, electrical and electronic networks, right? So basically, then what are the steps involved in estimating the Elmore delay? First, we derive the transfer function of the circuit. So if there is a circuit, we first derive the transfer function h of s. So let's first get the h of s. Once we have h of s, what we do is that we expand h of s in powers of s, right? Once we have expanded h of s in powers of s, then we simply collect the coefficient of minus s and divided by s, coefficient of s to the power 0, or the constant coefficient, or the constant there, and that gives me the Elmore delay. Right, so these steps, are these steps clear to you? For any network, we first derive the transfer function. We expand that in powers of s, and then we just collect the coefficient of minus s, and if the constant in that expansion is not 1, then we divide it by, or say normalize it by, that constant. Right, so often in passive circuits, your your output voltage would not be exceeding in your input voltage, and your output voltage would finally reach out to 1 in that case, right? So most often your coefficient of s to the power 0 would be 1, and you will get something like this. It is also possible to estimate the rise time as per the definition of Elmore. We are not going into that. If you are interested, you can refer to the original paper, where some interesting cases are also considered. In interconnects, we would not be requiring rise time, at least in the scope which we are discussing. Right, so with this, let us see, does this make sense? I mean, we have defined a new delay. It looks that okay, if I solve my circuit in the frequency domain, which is easier to solve, I can estimate something as the Elmore delay like this. Right, so let us see, does it make sense? So let us take a lumped RC circuit. This we know, we are very much familiar with the lumped RC circuit. So let's again take up a very simple circuit. There is a resistor R1 connected to a capacitor C1. Your input voltage is shown here and your output voltage is shown here. Now let us apply these 3 steps for a simple RC circuit like this, and estimate what is the Elmore delay. So before proceeding further, you should solve this on your own. Right, so I mean, the transfer function is simply known, V out by Vs, and in this case it would be 1 by C1s divided by R1 plus 1 by C1s. I can simplify this. When I simplify this, what I get is my H of s is simply this. This is very much familiar with everyone, I suppose. Now what we want to do, we have first step is done, right? So step 1, check, you have the transfer function. Now what is step 2? We want to expand this in powers of s. So let's take the binomial expansion. So H of s is equal to 1 plus R1 C1 s to the power minus 1. If you do the binomial expansion, you will get something like this. If you are not familiar that from this step to this step, how did you get? I suggest you check the binomial expansion for a general power. Right, so you will get something like this. You can check the basics. Now, if you have an expansion like this, what we have done is we have done step 2. So step 2 is also check that I have expanded H of s in powers of s, and then I have to collect the coefficient. So note that here coefficient of s to the power 0 is already 1. What is my other term? My other term is R1 C1. So this is my Elmore delay. Now this looks familiar. So this was our charging time constant for an RC circuit, right? So for an RC circuit where your output is an exponential, which we had seen in lecture 1, your Elmore delay is the same as your RC time constant, right? But this is only for a simple R1 C1 case, right? Now let us take another example. Let us suppose that my output voltage V out of t is given by this expression. So now I don't have a circuit, but I have an expression for my output voltage. So my expression is 1 minus these three exponents. Note that this is quite similar to the final solution which we had got for the diffusion equation. The difference is that in that case there were infinite summation terms. The number of terms in those summations were infinite, right? So here we have only three terms, right? So we had a summation like this there, right? Summation I going from 1 to 3 in this case. In that case your summation was going up to infinity, and all of these three different terms have different time constants. Now if you have an output voltage like this with just three terms, can you estimate the Elmore delay? So when I ask you to estimate Elmore delay, I am basically also giving you the information about input. So your input Vi of t is U of t, right? And I have given another additional information that A1 plus A2 plus A3 is equal to 1. Right. So with this, can you derive the Elmore delay for your V out of t? Right. So this is something which you should be solving on your own. Right. So you have to solve this problem on your own, the previous problem on your own, and also the derivation and how we got the expression for Elmore delay, or say the term of Elmore delay in the expansion of the transfer function, that also you should derive on your own. So here I will just finally give you the answer to this question, and the final delay, if you compute the Elmore delay, would come out to be A1 tau 1 plus A2 tau 2 plus A3 tau 3. Note that A1, A2 and A3 are the coefficients of these three exponential terms. You can see here that if I have a restriction or say constraint that A1 plus A2 plus A3 is equal to 1, then what I am essentially doing is that my Elmore delay is basically sort of an weighted average of the individual or say the RC delays or the charging times of individual exponential terms. Right. So suppose A2 is equal to 0 and A3 is equal to 0. Then in that case A1 will be equal to 1. What I have is a single RC lumped circuit, which I had seen in the previous example, and in that case your Elmore delay would be simply tau 1. Similarly with other terms, when there are multiple terms, what would happen is that your delay would be sort of an weighted average of this. So your delay would be dominated by the coefficient, or by a term which has the highest coefficient in your summation of those exponentials, right? So this is basically TD is a sort of a dominant time constant. So whichever is dominant, that would be there. If all three are there in equal quantities, I mean, then this would be 1 by 3, 1 by 3, 1 by 3, and then they would be like an averaged time constant, right? So I mean, you should solve this problem. You should be able to get to this expression, and in this week's discussion session we will look into it, and we will look at one more problem in this session. So I will stop this lecture here. I am stopping it before time, mostly because I want to give you time to derive this and the expression for the transfer function with Elmore delay on your own. So with that I will stop the lecture. In the next lecture we will see how this definition of Elmore delay helps us in defining the delay for an interconnect. Right. So with that I will stop here. We will meet in the next lecture. Good day.